So here we essentially have a arm throwing a ball. So let's draw the arm. We have a joint here, and then we have the arm here with a mass at the end of the ball, at the end of the arm rather. So mass here. And then we have this length, which is going to be the the length of the arm or the radius. We'll denote this as R sub A. And then we have this little segment here, which is going to be R of the joint. So we know that R of sub A, or the length of the arm, is going to be 31 centimeters, or 0.31 meters. The width of the joint will be, or the radius of the joint will be 2.5 centimeters, or 0.025 meters. The mass of the ball is going to be 1.00 kilogram. And then we have the final velocity of 8.5 meters per second. Then we have the delta t of 0.38 seconds. And we have the mass of the arm at 3.7 kilograms. So in order to approach this, we should first try to find a formula for the moment of inertia. So the moment of inertia is going to equal mRA squared, rather mR sub A, so essentially be the moment of inertia of the ball. So this ball right here is one arm's distance away from the axis of rotation. So that's why the moment of inertia is mR sub A squared, and then plus the moment of inertia of the rod, or in this case, the arm. So this will be I equals mRA squared plus the moment of inertia of a rod is simply going to be MARA squared over 3. So when applying the moment of inertia of a rod to this arm, it'll be the mass of the arm times the radius of the arm squared divided by 3. And this is going to equal, of course, 1 times 0.31 squared plus 3.7 times 0.31 squared divided by 3. And we know that I is now equal to 0.2146 kilograms per meter, kilogram meter squared. At this point, we need to find the torque needed to throw the ball, and this is going to be defined as the moment of inertia times alpha. Alpha can be found by taking delta omega over delta t, and this is going to be omega final minus omega initial over delta t. We know that omega initial is 0, so this is simply going to be omega final over delta t, and alpha is going to be, rather, we know that omega final equals simply v final over r. So we can say that alpha is equaling v over r delta t. And this is going to be equal to 0.31 times 0.38 as the denominator, and then 8.5 is the numerator. This is going to equal 72.156 radians per second. So if this is the radians per second squared, rather. So if this is the angular acceleration, we can find the force. So we know that the torque equals Frj. So at force times the radius of the joint, and the torque also equals I alpha. So that means that the force is simply going to be I alpha over the radius of the joint. radius of the joint, lowercase j. And this is going to equal I, which we found here, 0.2146 times alpha, 72.156, all divided by the radius of the joint, which is 0.025. And we find that the force is 619.387 newtons. So this is the force required in order to throw the ball, and then this essentially would be the moments of inertia right here. That's the end of the solution. Thank you for watching.